Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to have Junmi Ying as our speaker today. Junmi is a Lam Fellow of Computer Science School of Carnegie Mellon University. Prior to this, he's a PhD student and he was at UC Berkeley Computer Science Department. His advisor were Michael Jordan and Win Song. Junmi will stay here till Friday, and if you want to meet him, please drop me a note. By the way, Junmi will join the University of Arizona as a faculty.
So I would like to begin by thanking Danny for having me here, and nice introduction. So I just got in this topic of the network analysis quite recently, and I'm going to share some ideas on how to discover and explore overlapping community structures in large networks. And this is joint work with my collaborators Qirong Hou and Eric Xing from CMU. So, as everyone knows, so we are now living in a networked world, and networks basically are mathematics abstractions and the popular representations of complex systems, where nodes are individuals and edges are relationships between individuals. So they have been studied in social science, information science, biology, economics, and so on. So there are many interesting problems and questions in network analysis. So you probably heard about the power law distribution of the node degrees and the small world phenomenon and ranking pages and so on and so forth. So I'm going to talk about another important problem in network analysis, which is how to effectively and to detect community structure in a large network with the hope to identify like sets of the individuals with common functionalities, roles, or properties. And being able to do so will help us to understand and explore the networks more effectively. So let's look at some simple examples. So in social networks, the nodes are users and the edges are friendships. And based on the network topology or connectivities, so can we identify some social groupings, perhaps by their background or maybe by their interest? So in realities, each individual might belong to multiple communities, and its links will reflect this multiple memberships. So for example, an individual might be connected to colleagues, schoolmates, family members, and friends. And so unless that someone like who doesn't make friends with your family members or your colleagues, which I think is rarely the case, and then those community structures will be likely to overlapping with each other. Okay? And the second example is a protein-protein interaction network from biology, where each edge represents a physical interaction between two proteins. So in this case, each colored community is a functional modular that consists of a set of proteins with common functionalities. And because some proteins, like those red ones, actually they can have multiple functions and can play multiple roles in the cell, and those communities can also overlap with each other. Okay? So here's the problem statement. So given a large network, so let's just pretend it is to be large because I can only draw that size of network. So our goal is to find overlapping communities on this network, where nodes within the same community tend to have relatively dense connections compared to the nodes across different communities. Okay, And there are two aspects that distinguish our work from others. So first, because we're interested in overlapping communities, other methods you probably heard about, like modular optimizations and recursively recutting the graphs into pieces, so are not capable of doing so. And second, we are interested in large networks instead of smaller ones. Okay? So because each node I can belong to multiple communities, and we would also like to quantify its belonging factor by using this mixed membership vector theta I. So if there are k communities, then the theta I is basically k-dimension vectors lying in a simplex. So they sum up to 1, and then each entry represents the association strength of that node I with a particular community k. Okay, go ahead.
Can you explain that a little bit? Because, for example, I belong to my family.
Yes.
I'm a member of this community, and I'm also a member of MSR, say.
Yes.
So, what does it mean? You know, say there are the two communities, so
right.
I'm half here, half here. What does it exactly mean?
Actually, it's the meaning. The semantic meaning probably is based on the interactions that you interact with other people. So I will show that on later. Because that parameter mixed membership vectors only applies when you interact with other people. For example, if you have a majority of your friends from the family, then you probably have a large, the entry for the family community is probably larger than the MSR community, right?
I see. So it's not a measure of how much I'm a member of the community or how much of my interactions.
Yes, it's mainly
community.
realized by interacting with other people. So you will see that later on. Okay. Yeah. So because it's lying in a simplex, so we can use this pie chart to represent this vector. And in these networks, if you look at this one, this nodes and that node, they only belong to the single communities. So their pie chart is purely colored by the blue and the green. So if you use this 2D simplex to represent the communities, actually each corner of this simplex corresponds to a pure communities. Then the pie chart or the mixed membership vector of those two nodes should lie on the corner to represent the pure membership. Okay, but for those nodes in the multiple communities, their mixed membership vectors should lie in the middle of this 2D simplex to capture the overlapping communities. Okay, so our goal is to develop a statistical model and the computation algorithms to infer those mixed membership vectors for each node in the network just from the observed network connectivities or topology. Okay, so you want to get the topology to the mixed membership vectors. Is the statement clear? Okay. All right. So yeah. So this is a very fundamental problem in network analysis. So there are many applications can be thought about using this mixed member the community structures. So for example, if you can figure out the common properties of or common interest of users within the same community, then you can probably predict the popularity of the online content in the online, like a forum or network. And you can also use to detect the missing links. So for example, if two nodes, if there's no link between two nodes, but after analyze the data, you find that actually those two nodes are highly associated with a particular community, then it's very likely that this link is probably not correctly recorded in the data. Okay, and the next one actually is my previous work. It's sort of related because once you have the groups of the variables in the networks, you can use that information to actually to conduct group variable selections. So we have some previous work to generalize the group lasso into the functional setting. And last but not the least, you can simply just use it as a visualization tool to to explore the data, as I will show later on. All right, so the main challenging is scalabilities. So as the networks are getting larger and larger these days, and also it's because it's a conventional wisdom that larger networks tend to have more communities than the smaller networks. So the inference algorithms must scale linearly in both the number of the nodes n and the number of the communities k to be useful. So unfortunately, many previous formulation of this problems lead to intractable problems. For example, one of the probabilist method called mixed membership stochastic block models, the time complexity is quadratic in both n and k. So even for modest networks with 100k nodes, it actually will take several days to run. So our contribution in this work is to provide a scalable approach that scales linearly in both n and k, and our results show that we have competitive or even better results in terms of recovering known communities. And our implementation allows us to analyze networks with millions of nodes, hundreds of communities in just a few hours on a single multi-core machine. Go ahead.
So the assumption is that you don't know the communities. It's not only that you don't know the strengths of association of each participant.
Yes.
You don't know the communities.
Right. We don't know the communities.
So what is your success metric? How would So
you mean if you know the ground truth and if you recover something?
I don't know. Maybe you don't know the ground truth, but we can come up here with gazillion. I can associate just at random people to communities and that. How would you know that this one is better, this one is?
Well, for the real network where you don't have ground truth, you can probably just do some exploratory analysis, which I will show you on. But for the synthetic data where you have the ground truth, then you can use some metric to compare.
So you will discuss it later?
Yes, I will discuss that later. Okay. Yeah. Right. So another thing is you don't know the community structures, and by inferring the mixed memberships, like those dots in the simplex, then you can use that information to characterize the community structures.
But still, you have to, I can just do whatever I want and then say this is a community.
Oh yeah, I will show you the exploratory analysis, which is quite interesting. Actually, it's on this large IMDB co-star network, so it doesn't have a ground truth. It's just like two actors are connected if they appear together at least in one movie, and there's no prior structures on this network. And after running the analysis, you will find some interesting patterns. I will demonstrate that. Yeah. Any other questions? Okay. So our approach is based on the combination of two new ideas. So the first one is to build a powerful statistical model for a triangular characterization of networks. And the second is the development of a faster computational inference algorithm based on the stochastic variational inference. So let's start from the first idea. So in this talk, I will mainly focus on the undirected networks, but our approach can be extended to directed as well, with some extra efforts. So in the literatures, network characteristics are usually captured by this, if you have n nodes, then it's captured by this n by n adjacency matrix, where each entry tells you whether there's an edge or not between two pairs, a pair of nodes. So in contrast to this edge-based features, so our triangular characterization is based on the third-order network features, which we call triangular motifs. So each motif is a connected subgraph over 3 nodes. Okay, so if there are 2 edges connecting those 3 nodes, like this one, 2, 1, 3, then this is called an open triangle. And if they are fully connected, then it's called closed triangles. So once you enumerate all possible node triples, then you get this a bag of triangular motifs. It's similar to a bag of words for the documents. So we just use this bag here, the bag word here. Okay, so the major advantage of using this triangular characterization is it's about its compactness. So the number of the triangle motifs can be much smaller than the size of the adjacency matrix n squared. So just give you a rough ideas on about this compact characterization.
So by the size of the adjacency matrix, do you mean like a sparse encoding of it?
Yes, that's a very good question. Actually, you probably think it's not a very clever way to store your data using the adjacency matrix. You probably use adjacent list because that's more compact. But the answer is you can store that. You can store the graph, the original graph, using the adjacency matrix. It's a compact. But the problem is it's not about the storage. It's about the model. So if you want to build a model for this edge-based features, the statistical model still has to account for the probability of observing this 0 edges. So that means when you build the features, the feature itself actually is still n squared, although you can store it in a more compact way. So so probably that address your questions. Okay. Yeah.
So but actually in specific, the counts that you're giving are about the full size of the adjacency matrix.
Oh yes, yes,
okay.
that's n squared. Because if you, for example, if you want to use edge-based models such as a mixed membership stochastic block model, you have to deal with n squared, that kind of number of the features.
So could you explain a bit your motivation using triangular?
It's in the next slide.
Oh, okay.
Yeah. So let me finish this one. So I'll just give you a rough idea about this compact characterization. So in this IMDB co-star networks, about 900K actors, the number of the motif is 52 billions, but the adjacency matrix, the full one, is above 800 billions.
What is the complexity of calculating how many numbers of motifs are there?
Well, you only need to do that once. Although you had to enumerate all possible triples, but that only need to be done once. Yeah, it's just a pre-processing step. You can think it's like a feature selection step or something like a pre-processing step to extract the network features as a bag of the triangular motifs. You only.
I'm assuming maybe the complexity is like n squared or cubed.
It's n squared, but that only need to be done once. It's relatively expensive compared to the iterative procedures to estimate the parameters.
So then we will be able to apply to the networks like Facebook too big for your problem?
Well, we can deal with at least a millions of the nodes on the single computers. But that's probably a graph theory problem, how to do that efficiently, which we can think about that later. But right now, you can just think about the brute force enumerating all the triples. And maybe there are some steps that clever ways to save some computation at this step. But it's not a bottleneck of this of our procedure. All right. Okay. So here's the motivation for the triangular characterization. So actually, it is a basis for quantifying one important network feature called the clustering coefficient. So it's defined by the total number of closed triangles divided by the total number of open plus closed triangles. Okay, so in a social network, that quantity basically tells you what's the probability of two of your friends are friends themselves. So it's basically it's a transitivity property of the networks. Okay, so that quantity is defined in terms of just closed and open triangles. And the second motivation actually comes from the natures. So it has been shown that the 3 node connected subgraphs, they have been shown to be significantly recurring patterns in complex networks in nature and society, and that was discovered by a science paper about more than a decade ago. So although it's like a directed, but you can see that those they also call motifs. They call network motifs, and those motifs are 3 connected subgraphs. Okay. So empirically, actually, we can show that, as I will show later on, using these triangular characterizations, most of the community structures and the mixed membership information will be preserved by these features. Okay, and the only information that is lost actually is a set of disconnected node triples. Okay, but from the large-scale community detection perspective, they are probably less informative to find the community structures. Okay, is the description of the triangular characterization clear enough? Okay, all right. So now, given the network have been pre-processed, now we get we call data. So now data becomes a bag of triangular motifs. Okay, and the next step is to build its statistical model. So the assumption of our model is that the motifs are generated from a probabilistic process that includes the hidden variables. So there are several sets of the hidden variables, but the ones that we are most interested in is the mixed membership vectors of each node I, and those pie charts. Okay. So and our goal is to build the model to generate the data and then infer the mixed membership vectors from the data to capture the overlapping communities. Okay. All right, so because it's a probabilistic model, so you probably think that I will draw a very complex graphical model. So it's quite complex. So it's probably better to use a cartoon to illustrate this generative process instead of drawing a lot of brackets and notes. So let's assume that there are only 3 communities in the networks, so represented by this 2D simplex. And each node has a mixed membership vectors lying somewhere in this 2D simplex. Okay? And for each triple of nodes ijk, the first thing they do is to pick a particular mixed membership when they want to interact with each other. So that basically partially answer your questions is, although you have a multiple, you belong to multiple communities, but when you interact with someone else, you probably only have one particular communities at that stage. So that's basically, it's a context instantiation of the mixed members, the memberships. You can have multiple ones, but when you interact with other people's, you probably have one. And then that actually memberships can vary. It depends on who are you interacting with. Okay, and because this pie chart is lying in a simplex, so it's a multinomial parameter, so you can just draw this treat it as a multinomial parameters, right? And the next step is based on this combination of the communities, then we had to look up tensor parameters, which is indexed by the community structures. In this special case, it's indexed by this blue, red, and green communities. And at each entry of these tensors has a probability distribution over these 4 types of the closed and open triangles. Okay, and finally, based on this triangle generating probability, we generate a particular triangular motif for that node triple ijk. Okay.
Sorry, I lost you. So,
sure.
So here you have the motifs, which are just graphs, but you
Yes.
also, in your example, they are colored, right? So
yes.
So Can you explain that?
Yes, those colors are hidden variables. In reality, you don't have colors, you only have the patterns, the connectivities. And for example, the theta I, that is a hidden variables, and also the color is also hidden, right, in the data. And also this the tensor is hidden as well. So only have the observe the patterns of the motifs. The goal is to infer all the hidden variables using the probabilistic inference. Chris?
I don't understand how so the tensor takes into account just the motif or also the colors.
The tensor is a size of a k cube. It's indexed by the colors, which is the communities, right? But then each entry of this tensor has a probability distribution over all possible configurations of this motifs. And it's specifically for this combination of the colors. If you change the colors of those three nodes, then you look at another entries, then that tells you another probabilities for generating motifs for that combinations of the colors.
So this B, I can think of it as a function that given a set of colors,
yes,
and a motif returns a probability.
Well, actually, it only takes. You can think of it as a function. Only takes three. It has three arguments: the colors, and it returns a probability distribution over the motifs. It doesn't take the motifs itself. Yeah.
Is that invariant to permutations of the color?
Oh, that's a very good question. So although it looks like it's a k cube, if k is large, then you have many hidden variables. So as Chris pointed out, there's a lot of isomorphism problems. Like if two nodes are indexed by the same colors, then some two triangles becomes indistinguishable. And we have come up with a clever way to deal with that. So actually we can reduce the dimension of this tensor of size k cube to order of k. So actually just by sharing the parameters among certain combinations of communities.
And so you're also assuming that the number of communities is given some.
It's given, yeah. Right?
So before the motifs is like triangle over nodes.
Yeah.
Now it's like triangle over pure communities.
Well, it's still motifs over nodes.
Yeah, but why they have this pure color?
Oh, the color just it tells you when you interact with your friends or colleagues what kind of role you play during that interaction, and that's hidden.
But can it be interpreted as saying something that the probability is someone from community blue communicating with someone from community green?
Sorry?
How do you interpret that? So I thought that the implication is this is the probability of having an edge between someone in the blue community to someone in the green community.
Yes. So originally, if you use edge features, the mixed membership stochastic block models, that tells you, I draw a color, you draw a color. What's the probability that we have a edge between us, right? But now here we are dealing with triangles. So now the features is over three nodes. Then each of these three nodes draw a particular colors, and based on the color, what's the probability of generating this observed motifs? So the features becomes the motifs instead of edges, basically. That's just to summarize what the first part of our contribution. All right. Hope this already gave you some intuition how this generative graphical model is working. All right. So, but in reality, we only observe the back of triangle motifs. We just have these patterns. We don't have anything about the mixed membership vectors data that we care about most. We don't have this context-dependent membership vectors, the colors. And we also don't have the tensor parameters that represented the triangle generating probabilities. So a common way to perform the probabilistic inference is to first to assign a prior for each mixed membership vector because it lies in the simplex. So a common approach is to assign a dirichlet prior with alpha. And for each entries of these tensors, because it's also a multinomial parameters to generating probabilities, we also assign a common dirichlet prior. Okay. The goal is to compute the posterior distribution of those hidden variables. So there are 3 sets of variables. Okay, and using the Bayes rule. That's basically the Bayes rule. So what I described in the previous slides is basically setting up those probability for on the right-hand side. Okay. So this is a dirichlet, and this dirichlet, the theta given S is basically tells you what's the color I'm going to draw in these interactions, and this probability tells you what's the probability to drawing particular motifs based on the colors and the tensor parameters. Okay, so that's the quantity we want to compute. But the most interesting thing is the S, the mixed membership vectors. Okay, so it turns out that it's just like in many problems, probabilistic inference problems, it's intractable. So previously we have developed a approach based on Gibbs sampling. It has a complexity linearly in n due to the compact triangular representations. But because we use block Gibbs samplings, actually it's collapsed block Gibbs samplings, so we need to deal with this k cube here.
So is n referring to the size of your triangular representation?
So n is the number of n is the number of nodes.
Number of nodes. Then doesn't it depend on the size of your representation too?
Yes, so that's also a very good question. So actually in our previous work, we have something called a delta samplings. So delta sampling is basically like a local data reduction per step to preserve the local clustering coefficient of each node. And after the reduction, basically we throw out some triangular motifs. We can prove that the number of the triangular motifs grows linearly in the number of the nodes. Okay.
If you have k, say it's kind of a simple K in which I have n nodes, I have k clusters of equal size, and each cluster is just a clique, right? So the number of triangular representation is something like n squared. So you say you can drop it. Or
yes, it's a heuristic, I had to say, but it works pretty well in practice. So the idea is, if you have some nodes with high degrees, then you can see that the number of the triangles touching that node is pretty has a lot of triangles touching that node, right? But we come up with a step to basically there's a parameters that we want to choose so that we can make sure that the effective degree of that node is bounded by a constant. So then we can show that actually the number of the triangular representations after reduction grows in just linear in the number of nodes. But in practice, as I show in the IMDB, is still, even without doing delta sampling, is still much less than the number of the size of the adjacency matrix. But that's a very good question. All right, so for small number of the communities, this k basically can be treated as a constant, and then our methods has been proven to be faster and more accurate in terms of the recovering community structure than the edge-based model, MSB, which has a quadratic complexity in terms of the nodes. But it turns out that the Gibbs sampling becomes less useful for large networks. Like for 100K nodes and 10 communities, it converges pretty slowly. So then it comes up our second idea is based on stochastic variational inference. So how many of you heard about the variational inference in general? Okay, great. So we are after an intractable posterior distribution P. The idea of the variational inference is to find approximate distribution Q from the simple families to minimize the KL divergence between Q and P, where P is a true posterior. So a popular approach is to, it's called the mean field approximation, is to assume that the approximate distribution is factorized and parameterized by those so-called variational parameters. Okay? And it turns out that the minimizing the KL divergence between Q and P is equivalent to maximizing the lower bound of the log marginal likelihood of your data with respect to the variational parameters. Okay? So essentially, we cast a statistical inference problems to an optimization problems. So there are three sets of parameters, phi, gamma, and eta, and we have a lower bound of the log marginal likelihood that we want to optimize. And we want to optimize those parameters to make this bound as tight as possible. So that's the idea of the variational inference. So the variational inference basically is applying the coordinated ascent to optimize this lower bound. Okay? But actually, it's not scalable for large networks. So here is the reason why. So for each triangular motif, we have a variational parameter phi. And for large networks, there are a huge number of the triangular motifs, hence the number of the variational parameters phi. So this problem becomes very high dimensional to solve because this phi is very high dimensional. Well, fortunately, with a little bit of algebra and due to the structure of these problems, we can show that this lower bound of those three variational parameters can be decomposed into two terms. So the first term we call the global variational parameters, which governs the tensor parameter and the mixed membership vector theta. And the second term is a summation over all possible triangular motifs in the data. And that term depends on global parameters, eta and gamma, as well as on this phi ijk for each node triplet ijk. Okay. So, and we have a huge summation here. Okay. So now Lin probably know how to solve this problem effectively because we have a huge summation here. So the idea is to use a stochastic gradient method because we have a huge, large summation, but we don't want to do that. So before going to show the mathematical equations, so here's the intuition how this stochastic variational inference works. So instead of processing all the triangular motifs at each step to optimize their local parameters, we only subsample a set of motifs, a small set, and then we only optimize or infer the local variational parameters phi. And after optimization of those variational parameters, we somehow know the rough information about this color informations. And then we collected the sufficient statistics of those color informations, and we immediately update those global variational parameters. Okay? And then we keep iterating until certain convergence criterion is satisfied. Okay? So the intuition is that, for example, so if you want to estimate the mixed membership vector of an individual in a network, you don't need to examine all all the triangulars touching that motifs, right? So for example, if you belong to 3 communities, and if you want to know this person belongs to 3 communities, you probably only need to subsample a few your friends from each communities, and then you already know that this person actually have 3 communities. You don't need to enumerate all its neighbors. So that's the intuition why this algorithm works. Okay. So let's go that formally. It's an iterative algorithm. It's sort of like an EM algorithm. I have an E step and an M step. So in the first step, we randomly subsample a mini batch of S of all the triangular motifs from all the triangular motifs. And then we only update the local parameters Vij, okay, in parallel. Okay? And then we formulate these random functions. This function is random because it depends on the random set S that we draw from the triangular motifs. So the first term is still the global terms which you have seen in the lower bound, but the second terms only sums over all the triangle motifs that within the mini batch of the triangles that you sampled. And because you are only sum over a subset of motifs, you had to somehow rescale it. So M is the total number of the triangles. And you basically can show that if you take the expectation of this quantity here with respect to the S that you randomly sample, it's going to be the same as the lower bound that you want to optimize. So basically, we form random functions, which is much cheaper to compute because the reduction of this summation, but it's unbiased of your objective function, the lower bound you want to optimize. Okay. Well, the next step is you perform the natural gradient ascent with this unbiased estimation of the lower bound, and with some decreasing step size rho t. So the rho t has to satisfy these 2 conditions. So it's a pretty standard stochastic condition for the stochastic gradient method. And then we repeat this procedures until convergence.
So for natural gradient, it's unbiased. Do you need some like a rank 1? You first you come from the gradient, right? And then you have some rank 1 matrix multiplied before?
Well, the natural gradient basically pre-multiplied by the Fisher informations. Because you are dealing with the exponential family here. So Amari has a nice paper showing that using the natural gradient ascent works more effectively than the normal gradient.
Technically, the Fisher.
Oh, in that case, we can, because it's in the exponential family, we can compute that exactly. Yeah, and actually, that will simplify the update. Otherwise, you have something messy. Yeah. All right. So, and then our algorithm is guaranteed to converge to a local optimals due to a famous theorem by Robbins and Morone back to 1950s. Okay. Any questions about the algorithms part? I'm going to move to the experimental part. Okay. All right. So let's first look at the benefit of using the stochastic variational inference compared to the full batch variational. So we generate a synthetic scale-free network with 100 nodes and 10 communities. And because it's a synthetic network, we have a ground truth of the communities, then we can evaluate our performance in terms of the normalized mutual informations, which range from 0 to 1. So 0 means you completely mess up, and 1 means you perfectly recover the overlapping community structure. So this figure plots the NMI as the number of the data passes. And you can see that actually the stochastic variational with 10% mini batches converges to about 0.9 in just 1 to 2 data passes, where the full batch variational probably takes more than 10 data passes to converge. Okay.
So in that example, are the communities cliques?
Actually, it's we generated from the, some simulators. It's not necessarily a clique.
Is it? I mean, what's the basically how dense is the community versus the non-community?
Well, the community is not necessarily defined as a clique. So we have some ground truth, which is
density of edges. So
density of edges. I had to check about that.
What is the connectivity matrix?
The connectivity matrix?
Like, for one community, if you belong to the same community, you might have a probability of connecting with each other. If
Yes.
you belong to the different community, you might have another. Maybe for simplicity, you can assume like for all different communities, you have the same low probability of connecting.
Well, it's a scale free. It's not necessarily a block of the nodes with. Sorry. It's not necessarily a block of nodes with high probability connected.
But I'm assuming for your model, you have to do this diagonal dominant, like, if you belong to the same community, you might have a higher probability of connecting, right, in your adjacency matrix.
I'm not sure what, we probably can take that offline. Yeah. So, okay, for this synthetic network, we also have an animated demo. So we basically project all the nodes in the network into this polygon with 10 corners. Each corner represents a single pure communities, and the size of the circle is proportional to its degree. And let's just run it. So we keep track of this estimated of the mixed membership vectors theta I as our algorithm grows. And you can see that actually the results are going to be quite stable just after like about 10 seconds or so. And because in this network, there are significantly overlapping patterns of the communities, and you can see that there are significant amount of the nodes lying in the interior of these polygons to capture the overlapping community structures. And even for this result, the NMI, the measurement of the performance is still around 0.9. And I also want to emphasize that this is not a fast playing movie, and actually this runtime here is the real time on the single computer.
Is there a node in the middle, or is it just the center of the polygon?
This one?
Yeah.
This one, yeah. It doesn't have many connections, so the size is very small. So yeah. All right. All right. So that's for the demonstration of the stochastic variational inference. So we also conduct a series of experiments using two simulators. One is the mixed memberships stochastic block models, where the community is captured by a block of nodes with high edge probabilities. And also the second one is the scale free, where the communities tend to center at a high degree hop nodes. The baseline we're comparing is the MSB variational and also the Gibbs sampling version of our triangular models. So for each simulators, we generate a series of networks with increasing size n, and the number of the communities also grows as n divided by 100. The task is still the community recovery measured by this normalized mutual informations. So as you can see on the left figures, so our methods basically performs better than all the other methods across a range of the size of the networks. And there are a few dots for other methods because they fail to finish execution in a given amount of time. And this can be also seen from the runtime graph. All the other methods demand much more time than our methods. Okay. And the similar performance has been observed for the scale-free networks, and so our methods still performs faster and more accurate, especially on the large networks. So actually, you can see the interesting thing is for small networks, actually the edge-based model actually performs better, a little bit better than ours, and this one here. That's probably because for small networks, we extract the triangular features. Probably that for small networks, we throw too much information for small networks. But for large ones, that's probably less informative. All right.
These were all done with your 10% sampling?
Yes.
Did you try different sampling rates?
You mean the mini batch size?
Yeah.
We tried.
And does that change the results very much?
Well, it changed a little bit, but not quantitatively. Okay. So finally, I'm going to demonstrate our algorithms on this IMDB co-actor networks. So it has about 900K actors, and our algorithms converges in 40 minutes, just on a single 16-core machine. And we plot the top 20, I think 32K actors. The top means they have the highest degrees in the networks, and we project them into this polygon. And again, the colors and the positions represent the mixed membership vectors, and the size of the circle is proportional to the node degree.
So K equals 5?
Yes, K equal to 5 in this case. So we just start with 5. So I will show the larger K later on.
Kevin Bacon in the lower left.
Sorry, this one?
That Kevin Bacon.
Well, let me show you the next slide. Actually,
Oh, okay.
it's I think she's I don't know this actor very well. So, but basically, for each communities, we sort their. We just look at the top actors in each communities by their belonging factors. And for this community, actually, the top actors corresponds to they're all from this golden age of the Hollywood, and you can see that they have a long career span, and they have been active in many movies. And yeah, that's probably quite old, so I'm not that familiar with. All right, so the next one, this one, is European actors. So you can see they found the top actors from Sweden, Denmark, Poland. And this one is also very interesting. But because I think I'm being filmed, so I'm not going to list the actors here. But basically, you don't want your kids to watch their movies. So those two communities actually are less less characterized. So as you expect, that some actors, like for example this one, he is Polish and he was collaborating with Angelina Jolie in a Hollywood movie, and our procedures successfully recover its multiple memberships for this actor. Okay. Next, we increase the number of communities from 5 to 10, and you can see it actually allows us to examine the community structures in the final resolution. So, for example, the European community has been divided into subgroups based on their countries. So we have Sweden, German, Finland, and this is a set of singers from I think from Netherlands who participated in the TV competition. So actually, this top actor is obtained by thresholding this belonging factor at 0.8 and the degree to be 1500. But if you want to sacrifice a little bit about the belonging factor, if you decrease 0.5 to 0.8 to 0.5, and you increase the degrees to 3000, and then you will get this set of special actors again. And you can see this. Basically, I think this tells you that this k equal to 10, the resolution is still not finer to find. So this probably contains multiple communities nested with each other. So you probably need to increase the resolution again to find smaller communities. But this basically tells you this community still has multiple communities within it. So those actors are pretty productive in their career. It's like 3,000 movies. Yeah.
3,000 movies, right? If you're in a movie that has a big cast.
Oh yeah.
So if you're in 30 musicals, then you have a lot of weight. But if you're in a solo movie, you don't have a lot of weight.
Well, this degree basically tells you.
The cast of a movie is very small.
Oh right. Oh, you're right.
So it's if you're in big movies, so like the Bollywood movies, you should have huge degrees.
Right. But still, I think they're just pretty productive.
Writing papers.
I don't know. If you're a physicist, it's the physicist who has a degree.
All right, so
mathematicians will not show anywhere.
Yeah, so we also have a Brazilian, Japanese, like Indian, and actors from Russian rooted, and there's still a Hollywood and a Polish communities. So those results actually are pretty remarkable because we just take the raw data of the network without any prior knowledge about its structures, and our algorithm actually can find these interesting patterns from this large network.
So, when you were talking first on IMDb, these were not the categories that I would think of, right? So you would think about drama, action, comedies and stuff. But now when I look at that, right, so basically it finds geography or even more language barriers, right?
Yeah.
So
but actually this one is actually is not based on it's sort of based on the geology because they are from both they are all from New Zealand, but they also participate in a TV show.
Yeah, right? But my question would be, these clusters, how much overlap either between them? So I can imagine that the Swedish actor would not appear that often in a Soviet movie just because they speak a different language. Right?
Yes, but they will appear in Hollywood, as I will show you later, just in the next slide.
So did you quantify how much overlap?
Well, we haven't done that yet, but it's just actually it's a still work in progress, and we just start exploring this data.
How much if you just do a cut-based algorithm? How different the results?
Well, cut means it's disjoint, so you probably cannot find like overlapping structures.
Try to find the minimal cut. Would it find minimal cut and keep going, right? Build trees, but would it be much different than the result that we see here?
Well, then you cannot find these patterns if you use recursively cutting graphs.
You may check how much can improve from the minimal cut. That's what I'm suggesting.
So if you go back a slide,
sure.
Did you select again by having a high membership degree?
Yeah, I select both.
The same thing? So these are people who are exclusive in a community, basically. They have one dominant membership.
Yes.
And so it makes them look very good.
Right.
And so if you took somebody that has very weak membership, or find clusters of weak membership of something, I'm not sure what it would mean. But
well,
sure
then
you'll tell us more about these.
Yeah, then you probably, because for this large network, I don't think the 10 is the right resolution to examine all the communities. So, for example, here, if you want to sacrifice a little bit about the belonging factors, but then you will find something else, right? So, but
Keep going.
Yeah.
I wanted to make sure that you're using the same kind of selection procedure
Yes.
that gives you very strong numbers.
Right, right.
So from that point, I would guess maybe the more famous actors will actually have low edges. Because in a big shot, if they want to go to one movie, they will just earn lots of money and they don't make money. Each one will make them famous. But it's the supporting cast, who just, the guy who you never notice on the corner or walking on the street, those guys will appear in every movie.
Yeah.
That's,
Right, so the reason I just choose a high threshold for the belonging factor and a high degree is just to get a rough ideas about this, what does this community means. But I'm not saying that this community is exclusively like a Finnish or like something like that. So we still probably need some extra analysis to determine the community. Just like the topic models, examine all the top words in each topic, and then you somehow assign a semantic meaning, right? All right, so I'm going to finish soon. Right, so we actually on the Swedish and the Hollywood boundary, we find several famous actresses. So how many of you heard about Greta Garbo? Okay, yeah. So interestingly, we find that its belonging factor to Hollywood actually is much larger than the Swedish one. So, and then went to Wikipedia and find actually probably it's because she decided to sign the U.S. citizenship in 1950s. So basically she became U.S. citizens afterwards. And next is Ingrid Bergman, and she is famous in her performance in Casablanca, and also her belonging factor to Hollywood is a little bit larger than the Swedish one, because I think she is probably more active in Hollywood than in Sweden. All right, so finally I want to just outline some ongoing work and the future directions. So the first one is about how to determine the number of the communities. Okay, that's a hard question, just like how many clusters in the data. So you probably think about you can use cross-validation or maybe Bayesian non-parametrics, but it will be computationally very expensive for large networks. So it will be more effective to find a reliable method, simple methods, like maybe design some gap statistics to find a reasonable number for the number of the clusters. Second, so the data I'm working on is the raw data. So there's no meta information at all. So you probably can think about incorporate the node features and maybe the edge weights. For example, in the IMDB network, you can assign a weight to the edges to represent how many movies the actor or collaborate with each other in their career. Third, so in reality, I think the communities or networks are evolving, so will be significant to extend the current model and algorithm to the dynamic setting. And the last one is also quite interesting. It's a purely theoretical problem. So recently, Professor Peter Bickel from Berkeley has a set of nice work to study the consistency of community detections. But the model they study is a single membership model. But in reality, we already see that there are a lot of overlappings. So it will be very interesting and challenging to think about how to extend that theory to study the symptotic probabilities of community for the mixed membership models. All right, thanks. I will stop here and take questions.
So what do you think about incorporating kind of different types of edges in your model?
Oh yeah, that's where we're also interested, like assign edges.
Rather than assign, but you can have different types. They one was a director, one was an actor. You have the relationship between a director and an actor.
Oh, yeah.
Or, you know,
Actually, this IMDB network is extracted from the bipartite graph. If you go to the IMDB, it's like one layer is the actors, and another layer is the movies. But we just collapsed to co-star actors. So for that kind of network, you probably need to think about designing a new models for that. Because in that case, the triangular motifs probably has a different meaning, right?
I would find it interesting to try to formulate the objective here in a mathematical way, because.
All right, that's actually subject to debate a lot. So what do you mean by a community, for example?
For topical modeling.
Yeah. So kind of we make progress on problems without defining the problem and without defining the way we quantify success.
Right. So actually, if you go to the recent literatures by Professor Arola from Princeton, they already started to study the theoretical probability of the topic models. So for networks, and there has some work, but it's just for the single membership network model. Professor Bico. Oh, Arola.
he gave a talk. He was here just last week.
Last week, right?
Yeah.
I thought his work is about computational sense.
Was he talking about the topical models?
Did you? Yeah.
Right, yeah, talking about actually basically matrix factorization.
Right. So there are a lot of theoreticians starting to work on these problems. So yeah, I think right now I'm just starting to work on in an empirical way. So just to build the models and to analyze data. But as I said, there are a lot of interesting theoretical problems as well.
Okay, great.